Welcome to The Explainer. I am absolutely thrilled you're joining us today because we're going to tackle one of the most mind-bending, seemingly magical concepts in all of modern physics, the delayed choice quantum eraser. But look, we aren't just going to stay stuck in the realm of lofty, abstract theory today. Our goal is to completely demystify this whole subject by exploring a real, hands-on laboratory experiment. And the coolest part? It was built and analyzed by undergraduate students at the University of Portland. We're going to see exactly how these students took a massive cosmological thought experiment and put it right onto a standard laboratory table.
Okay, let's dive into this with a famous quote from the brilliant physicist John Archibald Wheeler. He's actually the one who first proposed the delayed choice thought experiment. He once said, "We, now, have an unavoidable effect on what we have a right to say about the already past history of that photon." I mean, wow. It's an incredibly provocative statement, right? It immediately hooks you with this mysterious, almost sci-fi concept. Could a choice we make right now in the present moment actually reach back and change a photon's past? It literally sounds like time travel. Well, today we're going to look at the hard data to see what quantum mechanics actually says about this. So here is our roadmap for today. We're going to cover the quantum choice paradox, erasing which-way information, the undergraduate experiment, building the delay, sorting the results, and finally, time and measurement. Starting off with Section 1, the quantum choice paradox, wave versus particle. To really grasp Wheeler's thought experiment, we have to look at two complementary observables. On one hand, we have interference fringes. This demonstrates wave behavior. When a photon's path through an interferometer is unknown, it acts just like a wave, passing through both paths and actually interfering with itself. On the other hand, we have which-way information, which represents particle behavior. If we somehow know exactly which path the photon took, well, then it acts like a localized particle. The absolute rule you need to remember here is that if the paths are, in principle, experimentally distinguishable through which-way information, those wave-like interference fringes, they vanish entirely. There's a very precise trade-off. You simply cannot observe both at the same time. Moving right along to Section 2, erasing which-way information, the quantum eraser. Now, to understand the eraser, we first need to carefully define what we actually mean by which-way information, because honestly, this is where a lot of the sci-fi myths originate. We need to myth-bust the idea of retrodiction. That's the idea that we are somehow changing the past. In quantum mechanics, when an ancillary particle, or ancilla, encodes which-way information about our primary photon, it does not mean the photon possessed a definite physical path in the past. This is absolutely crucial. Quantum states encode probabilities for future measurements, not definite past trajectories. If our ancilla lets us predict with certainty which path a photon is going to be found on, the paths are perfectly distinguishable, and we get zero interference. This brings us to a quote from Scully and Dreel that really serves as the thematic heartbeat of our entire explainer. It is what the experimenter can do, not what he bothers to do, that is important. You see, you don't actually have to physically measure the which-way information to destroy the interference pattern. The mere possibility of retrieving that information from an entangled partner photon is enough to totally obliterate the wave-like information. But, and here is the real game changer, Scully and Dreel realized that if you perform a specific measurement that permanently erases that which-way information, you can magically recover the interference pattern. Let's see how this works in practice. Section 3. The undergraduate experiment, from theory to lab. And this brilliantly illustrates how we transition from chalkboard theory to physical reality. The experiment uses a 405 nanometer laser diode. That laser fires into down conversion crystals, creating a pair of perfectly entangled photons. One of those photons, which we're going to call the signal photon, heads down the left path into an interferometer. The other one, the idler photon, heads down the right path. Because they're entangled, measuring the polarization of the idler on the right can actually give us the which-way information about the signal photon on the left. Let's walk through the exact steps the students set up here. First, that laser hits the down conversion crystals, creating our perfectly entangled signal and idler photons. Step 2, the signal photon passes through beam-displacing prisms. Now, because the path it takes through the prisms depends entirely on its polarization, its physical path is deeply, intimately tied to its entangled partner. Finally, step 3. The students use half-wave plates and polarizing beam splitters to manipulate the polarization for measurement. By just rotating the wave plate in the idler's path, the students can choose to either extract the which-way information or erase it completely.
All right, Section 4, building the delay, delaying eraser.
So to make this a true delayed choice experiment, The erasure measurement on the Euler photon absolutely must happen after the signal photon has already hit its detector and been irreversibly recorded. To do this, the students introduced a free space delay using 4 dielectric mirrors in the Euler arm. By bouncing the Euler beam back and forth between these mirrors, they literally force the Euler photon to wait. The Signal photon finishes its journey, it's completely detected, and only then does the Euler photon finally hit the wave plate where the choice to erase the information is made.
They actually engineered 2 brilliant ways to delay the photon long enough to beat the 8 nanosecond coincidence window of their detectors. The first was the free space delay we just talked about, which added 2 meters of distance, delaying the photon by 6.7 nanoseconds. It's conceptually very straightforward, but bouncing off mirrors causes beam widening and, unfortunately, photon loss. So the second method was a fiber delay. Instead of mirrors, they used 5-meter-long fiber optic cables right before the final detectors. Because light travels just a bit slower in the fiber, this achieved a massive 20 nanosecond delay and was highly efficient without losing photons. Both methods successfully forced the idler to arrive fashionably late to the party.
Section 5. Sorting the results, recovering fringes. Now, what's really interesting about this slide is what happens when we look at the data. If you only look at the detector counting the signal photons, you will never ever see an interference pattern. It just looks like a completely random smear of particle hits. Why? Because the possibility of which way information still exists out there in the universe. But when the delayed idler photon is measured with the wave plate set to erase, it generates a data key. This erasure measurement acts as a sort of sorting tag. When you correlate the random noise of the signal data with the specific detector clicks of the Euler data, suddenly 2 beautiful, perfectly out-of-phase interference patterns emerge right from the noise. The interference is mathematically recovered. It's like finding a hidden image in a Magic Eye poster. And that brings us to Section 6, Time and Measurement, the ultimate question. The definitive finding of this undergraduate paper, which, by the way, is perfectly in line with standard quantum mechanics, is this. The timing of the erasure is completely irrelevant. Let me repeat that. It doesn't matter. The students found that the physical delay, whether they used the mirrors or the fiber optic cables, made absolutely no difference to the measurement statistics. They maintained a 75% fringe visibility whether the erasure choice was made before or fully delayed until after the signal photon had been utterly destroyed at the detector. So the absolutely crucial point here is that we must dispel the time travel myth once and for all. No retrodiction occurs here. Measuring the idler photon in the present does not reach back in time and change the signal photon's past from particle behavior to wave behavior. As we just saw, the signal photon's data is always a random smear. It is only when we compare the 2 sets of data together that the pattern appears. You cannot use the idler to instantly communicate a change to the signal photon. This means the strict quantum mechanical no signaling principle holds completely firm. So we end with this huge, fundamental question. Does time order matter in quantum measurement? The definitive answer is a resounding no. The time order of measurements on separate entangled systems simply does not matter. The universe honestly doesn't care who gets measured first. The correlations are built right into the entangled state from the very beginning. It's a profound realization about the deep, strange rules of quantum information, and it was beautifully demonstrated by a group of determined undergraduates with a laser and some crystals. It really leaves you wondering, though, if time doesn't matter to entangled photons, what else about our everyday intuition of time and reality might just be an illusion? Keep asking questions, and I'll catch you on the next experiment.